Okay, why don't you go get your science notebooks if you don't already have them with you, because you will want to take notes based on this video. The last time we were together, we were taking a look at this test tube of different colors, and I'm not sure how well you can see that. Let me see if I can put something behind it that'll show up just a little better. But every time we started to play around with those colors, those colored liquids, we saw that they always layered out with the green at the bottom, the red next, then the clear, and then the blue. So there must be something special about the property of each one of those colors that allows them to always layer out that way. So here we go with an explanation. You may have noticed that all of the colors were in a gallon jug. That's important to keep in mind. One of the things that you need to keep in mind then is that all of the liquids had the same amount of liquid with them. So the blue had the same amount of liquid as the clear all the way across the board. So we say they all had the same volume. In this case, it was a gallon, but we're going to play in metrics, so we convert that to liters, which is 3.78 liters, but we really want that in a unit called milliliters. So that means there's 3,780 milliliters of liquid for each of those colors. Now, Caitlin thought that there was something added to the water. Not only the food coloring, which is what gave it the green, the blue, or the red color, but also she said there was sugar added. Well, there was something added to the water, but it wasn't sugar. It was actually salt. In the green gallon of water, I added 2 cups of salt. The red had 1.3 cups, the clear had 0.6 cups of salt, and the blue didn't have any at all. When I measured the mass of the salt that I put into each of those colors, we found out that the green had 577 grams of salt. The red had 375 grams of salt, and the clear had 173 grams of salt, but the blue didn't have any because it didn't have any salt. Remember that the volume was the same. So we can also begin to add together the salt mass and the water mass, and you can see the figures on the screen for each of the masses for each of those colors. So when you add those together, we end up with green having a total mass of 4,357 grams. You can see the others as well. We also remember that the volume was the same. So in this line of numbers above the white line, the top numbers represent mass, the bottom numbers represent the volume. And what we find out is that there's a special relationship between the mass of something and its volume. The way that we express that or say that, with the green, we could say that there were 4,357 grams per 3,780 milliliters. With the blue, we could say there was 3,780 grams per 3,780 milliliters. Anytime you hear the word per, that means we can do something mathematically to it, and that thing that we can do is to divide. So if we get our calculators out, which you don't have to do because I've already done it for you, we find out that if we divide these numbers out, so like with the clear, 3,953 divided by 3,780, we end up with a number 1.04, and the units are grams per milliliter. You can see what the number is for green. It's 1.15 grams per milliliter. The red is 1.1 grams per milliliter. And the blue is 1 gram per milliliter because the mass and the volume for plain water is the same. Let's think of this in terms of a number line. If we have a number line that starts with 0 at the top, and as we go down it increases, so then 1 and then 1.1 and 1.2 and 1.3 and 1.4. I just didn't have enough room to put all that on the screen. we see that the blue water ended up being at 1 because the number that we got when we divided the mass by the volume was 1 gram per milliliter. Clear was 1.04, which is a larger number than 1. Red was 1.1 gram per milliliter, which is larger than both the 1 and the 1.04. And the green is the largest of all those numbers, 1.15 grams per milliliter. So in terms of being larger, the green had the largest number, and we represent it on the number line like that. Think of it this way. We have 2 cans right here, and let's pretend like these cans are some kind of a round room, and each one of those dots represents a person in that room. So on the left-hand side, we have crammed 2, 4, 6 people into that room. On the right-hand side, we've crammed a bunch more than that. I'm not going to count them all up, but let's say there's 20 people crammed into that space. So if you think back what we just talked about before, the volume is the same. The amount of space is the same. We've just put more stuff into that same space. If you were a person, which of those 2 rooms would you be more comfortable in? Do you like having lots of people around you, or do you like having fewer people around you? That's a good question. You can ponder that for a moment as I flip to the next screen. So we call the amount of stuff in something its density. The density is the relationship between the mass of something and its volume. The amount of stuff in something and how much space that is in. So again, take a look at these sort of cylinders on the left-hand side. Compared to the right-hand side, there are many fewer dots in the left-hand side. So we say that the left-hand side is less dense than the right-hand side because there's more stuff crammed into the same amount of space on the right-hand side. Another way we would say that is that the right-hand side is more dense than the left-hand side. Another way to say that is we could say the right-hand can has a higher density. So that relationship between mass and volume is called density. Down at the bottom of the screen, you can see that mass and volume and density all have a relationship with each other, and we oftentimes define density as mass divided by volume. But we can also divide mass as density times volume. Or we can define volume as mass divided by density. Because there's a relationship here, we can do the mathematical equations on each of those. You don't have to remember that if you don't want to, other than you do need to remember that density is a relationship between mass, the amount of stuff that makes something up, and volume, which is the amount of space that material is taking up. So, again, as I mentioned, when we talk about density, we can use other word forms of density. So we use the term more dense or less dense because we're often comparing the density of one thing to something else. Let me give you another example of that. This is called a wave jar. There's 2 liquids inside this jar. One of them is clear on top, and the other one's clear at the, or excuse me, blue at the bottom. So we would say that the blue is what compared to the clear stuff on the top? And you would say it is more dense. That's absolutely right. We could also say that the clear material is what compared to the blue material. And hopefully you said it is less dense. Okay? So we can always talk in terms of density when comparing 2 things if their densities are different. One really cool investigation you can do at home if you want is to get a can of regular Coke or Pepsi, it doesn't really matter, but then get the diet equivalent of that. Take those 2 cans, one that's regular pop, one that's a diet pop, and then put them in a tub or a bucket of water and just see what happens when you drop the 2 of those in there and see if there's a difference in the density between the regular Coke and the Diet Coke. And I'm not going to tell you what the answer is because I do want you to go do that sometime. We also begin to talk about densities in other areas that we've been thinking about. We talked about low pressures and high pressures. One of the things I didn't talk to you about with high pressures and low pressures, especially when it comes to air, is the fact that we also have density playing into those kind of phenomena that take place. For example, we should all know that warm air rises. Well, why does warm air rise? Because it's less dense. It has fewer particles crammed into the same space that cold air has more particles crammed into. So we talk about cool air being more dense than warm air being less dense than cool air, and that's why warm air rises and cool air goes down. So think of other areas that we can begin to talk about density of materials. And when we come back together next week, we'll do one final activity that actually takes everything that we've talked about with pressure, with air pressure, and with density, and puts them both together in one activity that I'm sure you guys are going to like. So make sure you have that information about density in your notebooks, and I'll take a notebook check next week, and I'll see you on Thursday next week. Thanks. Goodbye.